Do we have any volunteers? Okay, I'm going to count the one, two, three. So let's not follow the same. 让他好，请说。
是今天的答案。
可以啊。
那0.732。
为什么？
因为它是2r平方，然后乘以3开的。
2r平方乘以3开根号。
然后再。
刚才什么那个什么？再讲一遍。
就是2r平方。
2r平方。
要乘以3。
乘以3。
开一个号。
开一个号。
就是对角。
等于对角。body 还是 base？ b 的20方。b 的20方。然后等于是2r加上。你已经把它直接等于对角线了，是不是？就把它低了，所以就等于是2，这样子吗？好，然后这样的结果就是这里直接开嘛，对，所以就是2r乘上根号3，等于是2r加上两边都除以2，所以就等于是根号3。是小，那大的是，因此根号3减啊，根号3就是1.732嘛，对不对？所以就是0.732。Okay, yeah, that's exactly the right answer. Don't worry, you might like what just happened, right? That's okay. Let's take a look. 好，我们一起看一遍哦，后面应该有，后面没有啊。Okay, let's take a look. So. If you take a closer look, you realize something weird. That is, what's this particular slice here? 我们切了这个蓝色这个 slice 哦，你会发现，我们刚才 artificial hole 不是也切这里 ？So if you take a closer look, you realize the slice we just took is identical to the slice. What happened to the artificial hole? That is, we slice along the body diagonal. But what happened here? 所以你会发现，为什么刚才在 introduce 的时候So you can realize that when I first introduced the holes, I introduced trigonal hole, tetrahedral hole, octahedral hole, and then suddenly we have a cubic hole. What just happened? Well, these 3 holes, trigonal hole, tetrahedral hole, octahedral hole, exist in closest packing. AB, 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 ABC, ABC, ABC. And what happened is, in the closest packing, you can have the choice where for a layer, we can fill in this really, really tiny hole, that is we call trigonal hole. We can also have the first layer kept by the second layer, and we form a tetrahedral hole. And lastly, we can also have a layer. Let me see something easy to see. We can also have a layer that is, say, let's look at this one. So this green appears. No, that's not this. There should be. Oh, this one. I don't know if you can see. This blue, and this blue, this green, this green, this green. So this is where our octahedral hole is. 1, 2, 3. 1, 2, 3. Right, so octahedral hole. Upright triangle and an inverted triangle. This is where our octahedral hole is. And then what you do is you slice, you tilt it and slice. That's indeed what we just saw here. So this is the green spheres. These are the green spheres, and these are the blue spheres. So we tilt ABC, making it put it into octahedral hole. But what really happens here is we might not have closest packing, but we can still have body-centered packing or single cubic. That is, in our unit cell, we are not in the closest pack. 所以在这里，我们不是在 A B B A B， 也不是 A B C A B C A B C， 为什么？因为你的 metal 就不是在最 ideal 的 packing。比如说什么？比如说 uranium， 比如说什么？比如说 polonium， 他们并不喜欢 closest packing。那这跟它的 metal 喜欢有几个 neighbor 有关系哦。我们这堂课就不讨论。Okay. So what really happens is right now in our unit cell we don't have closest packing. It's not in the hexagonal closest pack. It's not in the face-centered cubic. It's in the simple cubic. So it's the same. we are still slicing along the body diagonal, right? It's the same slice as the body-centered cubic, as in the octahedral hole of base-centered cubic. 但是差别在哪里？差别在 octahedral hole 这4颗是碰在一起。So in octahedral hole x1, 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 x1 along the body diagonal will touch each other. 因为这是一个 closest path， 所以它们是碰在一起。但在 simple cubic, what happens in simple cubics? They don't touch each other identically. It is actually in a simple cubic, and you squeeze it out. Right now, it becomes a rectangle. So if you look at this one, I don't know why this. Give me something new. So this is right now a rectangle instead of a square. So it's almost identical to octahedral hole, but right now it's in a rectangular environment instead of square environment. Hence, when you slice it along the body diagonal, it's that is one of the edge is shorter, the other edge is actually longer, and such that the body diagonal is big R plus small r plus small r plus big R. And what happens is, then how do you get the face? Well, you already know how to get the face. That is h plus h, right? Because it's a simple cubic, it still touches along this face here, along this face here. And we are just looking at the body here, right? So in order to get the h is just r plus r, but the face is r squared plus r squared equals to base squared. Hence, let me quickly do it. 看来我们这两个上不完了。Okay, let me quickly draw it. Right. So you can see that this is a base. This will be this base here. And this will be h squared, h squared. And of course they touch each other on the face. Super up. And of course this is R. And right now what we want is we want this whole thing. And it's going to go up. This is the third dimension. And this is what we are solving for. Okay. And this long face is just h squared plus h squared. So now we can equate. This rectangle is base squared and h squared. That's indeed what's shown here. So the horizontal plane here is actually the face square, and this is just the height of the cube, right? And it's like this. Now we can solve for it, right? So big R, small r, big R. And this is a rectangle, so it's still right triangle. Just it's no longer an equilateral triangle. The two lenses are not the same, but it's still right triangle. Right? So Pythagorean theorem will still work. That is h squared plus face squared equals to body squared. So body squared equals to h squared plus face squared. And we know face squared is just h squared plus h squared. It's h squared plus h squared. And we know they touch along the edge, so edge is r plus r. 3h squared equals to 3, 2r squared. Okay? And we know that the body is just r plus small plus r, big R. Equals to 2 big R plus 2 small r squared. Alright, centric. Square root on both sides. And it's going to go right here. So square root of 3 multiplied by 2r. Will be square root of this. And this is just 2r plus 2 small r. Centric. Divide. Centric. Subtract both sides by r. And square root of 3, 1.732. So subtract out by 1, so 0.73. And we have done. Okay. So the only thing you need to realize, different from octahedral hole, we are no longer at a square when we slice it. It's a rectangle when we slice it. Hence, one of the edge is actually longer than the other one. Hence, that's why the number becomes larger. For octahedral hole, it was square root of 2, right? Because this edge is shorter. For a cubic hole, it's longer because face is longer. For tetrahedral hole, we are connecting along the face diagonal. Face diagonal is 1. Hence, we can summarize. That is, hence, we can summarize, and you need to remember this. That is, for cubic hole, is square root of 3 minus 1. For octahedral hole, it's square root of 2 minus 1. And for tetrahedral hole, it's square root of 3 over 2 minus 1. Right. And the number, if you evaluate this, is 0.14 and 0.25. Okay, and you need to memorize these 3. Tetrahedral hole, minimum of the size of the small radius to the ratio of the large radius. The minimum of the size of the small radius to the largest radius. It can only be greater than this, cannot be smaller than this. And the minimum of the size of the small r to the big R almost identical. Right? 0.7. 好，这3个数字要背哦，一定要背，一定考不好。好。Yes, that was exactly correct. So hence, the radius of the small r equal to 0.732 big R. Hence, we can summarize. If the small r, well, if the question give you 2 radius, so the small r is like, say 1.0 angstrom, and the big R is 1.5 angstrom. Right? The ratio is going to be around 0.7667. Then it's going to fall within octahedral hole. If the question gives you 0.5 and 0.15, well, 0.5 divided by 1.5 is 1/3, right? It will be 0.3333. It's going to fall into octahedral hole. And the question is give you 1.2 over 1.5, then it's going to be how much? 0.8. Well, it's going to fall into octahedral hole. That's one way the question could test you. Okay. 好，那这些数字要背哦，所以这个每一个我们刚才 derive 出来的数字都是 lower bound，都是 lower bound。Okay. Alright. Then after that, how many do we have? 在一个我们现在知道了，它随便我给你一颗新的 atom， 那我知道它要放在哪里，但是它可以放几，对不对？我有在一个 unit cell 里面，我有这么多空间，我有这么多 holes， 那我们每个可以放几？ So now you can imagine, we know given an atom, where should we put this atom? In the trigonal hole, trigonal hole is we didn't discuss. In the tetrahedral hole, in the octahedral hole for closest packing. Now of course, if this were not closest packing, it's simple cubic, well it's going to be occupied by the cubic hole. But how many are there? Well, for a cubic hole, there's only one. Right inside the body center of this cube. And after filling this cubic, it looks like a body center cubic. Well, for different packings, you're going to have different number of holes. For body center cubic, you can imagine that this is body center cubic, right? So here, this is the cube, and we have body center. How many octahedral holes can we have? We can have one on the face, another on the face, another in the back, or the face in the back, another face on the left, another face at the bottom, another face at the top. So we know for a cube we have 6 faces, so we have 6 octahedral holes. Right. And again, for the edges, they can also form octahedrals, right? So you can imagine that these will also form octahedrals on the edge. Why? Because you can imagine that these 3 is going to form one side of the octahedral, and we have another 3 that will be coming out of the edge. Right? So it's going to be one here, one here, one here. A little bit hard to see. But remember, these holes are not complete because it's sliced into half. So that means in the face, every hole is shared by two surrounding unit cells. So for BCC, where the artificial holes are on the face, we have 6 divided by 2. We have 3. For edges, it's shared by 4 unit cells, right? Can you imagine that? 1, 2, 3, 4 will share this artificial hole. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 artificial holes shared by 4. So we have 6 shared by 2 and 12 shared by 4. Maybe actually, right? So we have 6 artificial holes for body center. Again, we have 6 faces. 1, 2, 3, 4, 5, 6. These 6 faces are shared by 2 unit cells. So we have 6 artificial holes shared by 2. In addition, we have 12 edges. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12, 11, 12. Shared by 4 unit cells. So 12 divided by 4. So we have 6. 3 and 3. So we have 6 artificial holes for body center. Right. And we also have tetrahedral holes. They are a little bit hard to see. They are right here. Every face we have 4 tetrahedral holes. We have 4 tetrahedral holes. And why? Because you can realize that you have one here, and you can imagine that. Let's see. How do we form this tetrahedral hole? Yes, you have another sphere here, another body here. So this body, these 2 edges, and this body forms a tetrahedral. 如果再画出来的话， So this is one of the edge. This is another of the edge. This is the body, and we have another body on the top. So this will form a tetrahedron. I don't know if you can see this. 这我看得懂吗？ You guys, can you guys see the tetrahedron here? There's a bit argument. 对，这是 BCC 的 body center， 这是另外一个 BCC 的 body center， 对不对？它上面有个 retaining unit， 然后这是它两个 edge， 对不对？所以它就是 tetrahedron。所以两个 edge， 两个 body， 所以 tetrahedron 就长这样。So you can see that this is the 2 edges, this is the body, and that's how you form a tetrahedron. That is, you basically put 2 lines perpendicular to each other, and you connect all the vertices, and you form a tetrahedron. So that would be how you form one of the tetrahedrons here. And you can do the same trick with these 2 edges, form the same tetrahedron, and these 2 edges will form another tetrahedron, and these 2 edges will not form another tetrahedron. That's why we have 4 tetrahedral holes. And same trick on this side, right? You can have 4 tetrahedron here. Body, another body, the edges form tetrahedron. Again, body and body, but with these 2 edges, so we form another tetrahedron. Body, body, with these 2 edges, so we form a tetrahedron here. And body, body, with this edge, form a tetrahedron here. That's why we have 4 tetrahedrons here. That's how. Alright, and let's sum this up. And if you cannot picture this, please go back and actually try to draw the tetrahedron. Oh, actually, it's from here. So body, body, edges here, so you can see it. If you cannot see this, please go back home and then read this slide again and try to use your imagination, or try to Google, see if you can find any 3-dimensional models. Right? So how many tetrahedral holes? Every face we have 4, right? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. And each of this is shared by 2 unit cell. 24 shared by 2 is 2. Please remember this number for body center cubic. You have 6 artificial holes. 3 on the face, 3 on the edge. You have 12 tetrahedral holes. 12 all on the faces. Right? So you can see that the phase are busy. Either they have small tetrahedral holes or they have one octahedral hole. Really depends on if your sphere is small or large. It's going to go to the octahedral hole, it's going to go to the tetrahedral hole. Depends on the size. So immediately you can see the ratio between octahedral hole and tetrahedral is 1 to 2. Octahedral hole to tetrahedral hole is 1 to 2. And this persists as we go to other cubic systems. 这个 ratio 是不变的哈，1:2，1:2。等一下我们会看，那其实你也能理解了，因为一个是什么？一个是0.225嘛，一个是0.414。You can understand this, right? Because this is 0.414. This is 0.225. If you double this number, it's roughly 0.43. Right? So every cubic hole is twice as big as a tetrahedral hole. So if this sphere is small, it can fill 2 because it's only, each of them only occupies 0.25 of the whole volume. If it's octahedral hole, it's going to occupy 0.414 of the whole volume, and you occupy only half as much. 等一下这个 ratio 会 persist 哦，而且考试就会考。Okay, then we're going to move on. Everyone follow me? 这有问题吗？这个确实开始进到真的需要花一点想象力的地方哦，因为它们是三维空间嘛。It's three-dimensional, so it requires your imagination. Next one is FCC, right? Face-centered cubic, and again we have a lot of octahedral hole and tetrahedral hole. Right. So face-centered cubic, we have the cube. All the vertices occupied, and then we have the 6 faces occupied by the original sphere. And now we are putting another type of sphere into the lattice, the unicell. So of course you can see in the middle body center we have octahedral hole. Right? It's not too hard to see this is octahedral. And just like a body center cubic, all the edges are also octahedral holes. So it's not too hard to see for you that we should keep this one, but we reduce this one. Right? So for face-centered cubic, what we have is all the edges are shared by 4, and we have 1 in the body center, right? So it's going to be 1, and plus 12 divided by 4. So we only have 6 octahedral. Oh, not 6, sorry, 4. 4 is FCC. And tetrahedral holes, well, you can see that inside the unicell, there are already tetrahedrals formed by 2 of the nearby faces, 3 of the nearby faces kept by 1 of the vertices. 所以在 FCC 里面，你拿3个邻近的 face， 它们就直接封一个 triangle 了，对不对？3个邻近的 face 封 triangle。接下来怎么样？接下来那个 vertex， 那个其中一个顶点刚好就是那个 triangle tetrahedral hole 的正常方，所以它就是一个 tetrahedral hole. And of course, you can have multiple nearby faces in a pair of 3. This one, 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 right? This one, this one, this one. So every peripheral with the top face can form 4 tetrahedrals. 1, 2, 3, 4. And they are kept by these 4 vertices. And it will be the same for the bottom, right? So 1, 2, 3. 这3个will form a triangle kept by this. 1, 2, 3. Form a triangle kept by this. 1, 2, 3. Form a triangle kept by this. And 1, 2, 3. Form a triangle kept by this. So you can imagine we have 1, 2, 3, 4, 5, 6, 7, 8. 8 vertices that can actually kept the triangle. So we have 8 triangle holes indeed. We have 8. And what are they? They are simple cubic. This is really interesting, as we'll see examples. This is what we call the anti-ferrite structure. It's an anti-ferrite structure. Later on we'll see examples. Don't worry about it yet. It's called the anti-ferrite structure. That is, the anion or the cation actually form a simple cubic, surrounded by the anion or cation form face-centered cubic. This is one of the really common latest crystal ionic compound that we have a special name for it. It's called anti-ferrite. We'll see XMLs, don't worry. And as you can see, these 8 tetrahedral holes are within the unit cell. They are not shared, so we have 8. Again, 1. Right. So this ratio does not change. But you quickly realize we have fewer spheres, right? 6, 12, 4, 8. Why? Well, FCC is one of the closest pack, right? So most of the cubic is already occupied by the yellow spheres. There's not much space inside the lattice for the small sphere to come in. That's why we have fewer number of holes. Body center cubic is not the closest pack, right? The density is 0.68, not 0.7. And of course, this does not finish yet. We have one last one, right? We have HCP. So last one, then you can start remembering all these holes. 好，那大家能猜到吗 ？HCP 是什么 ？HCP 是 AB packing。HCP 是 AB packing, one of the closest pack. And previously, FCC is another closest pack. It's ABC. Both of them have the same packing density, 0.74. So you can imagine whatever is going to apply to FCC is going to apply exactly the same to HCP. Indeed the same. But caveat. 当我那时候在一开始在教这个 crystal system 的时候，我特别讲到 ，if you remember from the table that at the end of the crystal system we have SC single cubic, BCC bicycle cubic, FCC basic cubic, and hexagonal closest pack HCP. If you look at the number of atoms inside the unit cell, it's 1, 2, 4. So simple cubic has 1 effective atom inside the unit cell. Body center has 2. We have another one in the body center. Face center we have 4. However, hexagonal closest pack, even though it's another closest pack, we only have 2. Why? Because the volume of the unit cell is half of that of HCC. So you can imagine everything will apply the same to HCP with half of the numbers, because the unit cell is just half of the size. So can I erase BCC? 我可以擦掉 BCC 吗？大家都 OK 吗？好，有抄下来吗？也就是说，基本上任何在 FCC 的，你只要除以2就好。So anything that applies to FCC, all you need to do is divide that by half. So for HCP, tetrahedral hole is 2, and tetrahedral hole is 4, and the ratio is going to be the same. Why? Because the unit cell is half as large, so you can only fill half of the number of atoms. And you might ask the question, so how do you come up with this? Well, yeah, let's do it very quick. 所以在这里你可以看到，这里面是一个 lattice. So the hexagonal prism here contains 3 unit cells. Now what? 3 unit cells. This is one of the unit cells with a prism here, paragon here. Another unit cell with another paragon here, and the third unit cell with the paragon here. Why do we need to multiply this by 3 instead of looking at 1 unit cell? Because this is not a cube, it's very hard to picture. But if we actually make it bigger such that it's a hexagonal prism, it's much easier to see. Hexagon is much easier to see. Now in this hexagon we have 3 octahedral holes here. In this hexagon here we have another 3. 3 on the top, 3 at the bottom. Total is 6 octahedral holes shared by 3 unit cells. So it's 6 divided by 3. Divided by 3 because there are 3 unit cells. And how do you see this? You can see that this one is really formed by, it's really formed by these ones. 2 here, 2 here, 2 here. These two actually will form the octahedron here. So the octahedron will have, let's see. Yeah, that's a little bit hard to see. And for the tetrahedral holes, it's going to be the same. Instead of having 6, we are going to have 12, right? Divided by 3. So that is, we have 2 on the edge, and we have 6 edges. Then we have 2 in the dumbbell here, and then we have a bunch of this already inside the tetrahedrons. They inside the lattice. So we have, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 on the edge, and one, two, three, 4, 5, 6 inside the lattice. So that will be 6 plus 12 on the edge, and each edge is shared by 3. And we have 2 inside the dumbbell here. And this whole thing is divided by 3. So this will be 6 plus 4 plus 2 divided by 3. That will be 8. 这个有点难看得懂，这个因为这个结构稍微比较凌乱一点，因为它其实是有3种不同的 tetrahedral holes， 一种是在 edge 上面，一种是刚刚好在正中央这边，一种是环绕着这个 lattice 里面，有点类似这样子的，还有3个在这边，所以其实不是那么容易看，那也没有关系，你也不用真的把它看出来，你就把它背起来就可以了。It's a little bit hard to see because we have 3 types of tetrahedral holes. One type on the edge, another type right inside the small triangle on top of the bottom of the small triangle, and the other type is actually surrounding the unicell. It's a bit hard to see. That's fine. Please just remember this number. 这部分非常难，因为这部分很难，它是一个3D 结构，很难看出来。那没有关系，你把数字背下来就好。Please remember the numbers here. If you don't follow and you really want to understand, please go back home and you can look at the structures again and again until you actually distinguish the 3 different holes here. 3 different types of tetrahedral holes. Summarize. Octahedral hole. For FCC, we have 4 octahedral and 8 tetrahedral. FCP is only half of the size of FCC, so we only have half of the amount, so we have 2 octahedral and 4 tetrahedral. But regardless if it's FCC, BCC, or SCP, the ratio between octahedral hole and tetrahedral hole is always 1. And that is due to the required radius of the small sphere to the large sphere. And why do we learn all about this? Because we really want to understand RD compound, right? For example, sodium chloride 最常见的这个就是我们说的盐巴，对不对？ sodium chloride is FCC inside FCC. That is, if you imagine the green spheres are sodium cation, what happens is every chloride anion will occupy the octahedral holes of the sodium anion. So the sodium cation forms FCC, single cubic, face and cubic, and as I already mentioned, on the edge we have each octahedral hole shared by 4 unicells. 4 unicells and 4 unicells. And we have 1 inside the body center of this FCC. These are occupied by chlorides. And chloride itself also forms an FCC. So in this case, we will say chlorides occupy the octahedral hole of FCC lattice formed by sodium cation. And you can understand this by directly taking the ratio, right? Sorry, I said it the opposite. The chlorides form the unicell and the sodium will occupy the octahedral hole. It's actually the same because they are both FCC. So if you look at the radius, sodium cation will have a radius, ionic radius of 102, and the chloride has an ionic radius of 181 picometer. And if you divide sodium divided by chloride, you get 0.564, which is right between 0.414, the lower bound for octahedral hole, and the upper bound, the lower bound for cubic hole. So that means sodium will occupy the octahedral hole formed by the FCC lattice, FCC unicell of chloride. And another type, so we just mentioned about sodium chloride, another type is called zinc sulfide. ZNS, and this is a really interesting material, right? It's a really good semiconductor, right? Not quantum dot. I'll talk about it, alright? And if you look at this, zinc is right here. Zinc 2 plus, RE grade is 74. Sulfide is here, RE grade is 184. If you divide, you get the ratio to be 0.35, which is right between 0.224 and 0.414. So from this table, you predict zinc sulfide, zinc will inside the tetrahedral holes, Again, it's FCC and tetrahedral holes, and as I already write down here, FCC has 8 tetrahedral holes. But then you quickly realize one thing. If zinc occupies all the tetrahedral holes, that means inside these lattice will have 8 zinc. But for FCC, the effective atom number for sulfide will be 4. So that means the ratio is going to be 8 to 4 or 2 to 1. So that means the empirical formula should be zinc 2, sulfide 1. That will be wrong from what we observe chemically, and the charge will not be balanced. So what really happens is zinc only occupies half of the tetrahedral hole. So this is again the unicell formed, the FCC unicell formed by sulfide S2 minus, right? The face center cubic. And we have 8 tetrahedral holes, right? 1, 2, 3, 4, 5, 6, 7, 8. Right? They form a single cubic sitting inside our FCC. But because of the charge, we cannot actually have 8 zinc inside because we only have 4 sulfide. So what happens is zinc occupies every other side. 1 missing, 2 missing, 3 missing, 4 missing. Right? So it only occupies 4 out of these 8 tetrahedral holes. Why not occupy the octahedral hole? We have 4 octahedral holes because it's too small, right? You cannot actually hold the octahedral hole together. Alright, follow me？ 这部分有懂吗？好，那前面我花了很多时间铺陈什么？铺陈 FCC 跟 HCP 根本就一样，我不能说一样，但是它们的性质很像。Previously, I spent a lot of time talking about the similarity between FCC and HCP. Why? Because they are both closest packed. Their packing density is 0.74. They share many similar properties. The amount of holes are the same, 4, 8, 2, 4. It's only because this is half of the unicell, half of the size of FCC. So indeed, zinc sulfide has another isoform, isomorphism. Yes, another polymorphism. 它有另外一个 phase。那 phase 是什么？那 phase 就是怎么念来着 ？Wurtzite。前面那个叫 zinc blend. Sorry, I forgot to say. This is called zinc blend. So this structure, if sulfide inside FCC and zinc occupies half of the tetrahedral hole, it's called zinc blend. And zinc sulfide has another phase. It's a polymorphism. It's called Wurtzite. That is, sulfide actually form HCP, and right now we have the zinc occupying the tetrahedral holes inside HCP. So again, we have 4 tetrahedral holes, and the zinc is going to occupy half of this. And if you look at this structure closely, you're going to say, no, the gray should be zinc, and the sulfur should be yellow. So this is actually zinc forming HCP, and sulfur occupies the tetrahedral hole. Well, both statements are correct. Both statements are correct. Why? Because if you enlarge, you realize sulfides are also in HCP. 所以这就是一个 HCP 的 sulfide， 然后中间 fill in HCP 的 zinc， 所以你不管看谁都是 HCP 的。那刚刚好，怎么样可以封 HCP 呢？就是当你 occupy 一半的 tetrahedral hole 的时候，你刚刚好就是一个 HCP。那还记得之前讲 HCP 怎么样吗？之前讲 HCP 就是 AB 嘛。那怎么样封 AB？ 就是我把每一层6个 hole 填一半，所以这就是为什么，因为6个 hole 都是 tetrahedral hole 嘛，那我只填一半，所以就是 HCP。Okay, let me actually repeat the English very quickly. This is something really interesting about crystal lattice. That is, remember what's HCP? It's AB pattern, right? AB, so A, B, A, B, A, B, A, B. They are shifted by I don't know how many atoms. And how do we form AB packing? Well, every layer we have a sphere surrounded by 6 spheres. That means we generate 6 holes. These 6 holes are occupied by 3 holes by the second layer. Right? The second layer will occupy these 3 holes. And that's indeed the tetrahedral holes here. We have 6 tetrahedral holes, and we only occupy 3 out of these 6 tetrahedral holes. And that's how we actually have HCB, HCB, HCB. So you can imagine you have an ABABAB packing of zinc 2+. You have another ABAB packing of S-, and you just push these 2 together, and you get wisdom. Okay, I know that's a lot. And the consequence of this is the phase diagram of zinc is really interesting. That is we have 2 phases. At low temperature, we have zinc blend. That is closest pack in FCC. And we have 8 tetrahedral hole, and then we occupy 4 out of these 8 with zinc. If you increase the temperature, this system still want to pack closely, but you want to have high entropy, so it becomes wozite. Still closest pack from FCC facing the cubic system, closest cubic system, cubic closest pack CCP, shift to HCP. Right? Still closest pack, but the unit cell right now is no longer cubic. It's tilted such that it becomes longer. Right? So it's wozite. So you can see that both of these are actually phases of zinc sulfide in different crystal lattice. Right? One is FCC, one is HCP. So that's why I spend so much time on FCC and HCP, because they are almost the same. They are thermodynamically equivalent from each other a lot of times. And of course, when the ratio is wrong, you just have some sulfide edge crush out something. Anyway. And lastly, let's see how much time we have left. We have 20 minutes. Okay. Another one is when we have even larger ones. That is calcium fluoride. So the structure of calcium fluoride, again, you can see that these are a bunch of calciums. So we have FCC calcium, and then all these tetrahedral holes are occupied by fluorides. And the ratio is actually 1 to 2, so all the tetrahedral holes can be occupied by fluoride. Zinc sulfide 是1:1嘛，所以只能 occupy 4个。那现在 calcium fluoride 是1:2，所以我可以把8个都填满。那8个都填满就是什么？就是一个 simple Q。那这个结构有个名字哦，它非常非常的 famous。为什么？因为你发现很多的 fluoride compound 都是这样 ：strontium fluoride、barium chloride、lead fluoride、cadmium fluoride。A bunch of fluoride compounds crystallizes in this ionic compound in these layers. Hence, we have a special name for it. Okay. Oh, sorry, it's called fluoride structure. It's called fluoride structure. That is basically compounds of fluoride. Compound of fluoride. Well, MF2, mostly fluoride structures. And this is formed by phase the cubic of the cation and single cubic of anion. Basically, the anions occupies the tetrahedral holes inside this. And we can take a look to understand why. Well, calcium is 100%, 100. And fluoride is 133. So if you divide these two, you realize this number is 0.752. 752, which is greater than 0.732. 所以这在一个 cubic hole 的 category， 但是我们在 closest pack， 我们们没有 cubic hole。cubic hole doesn't exist for this structure because we are not in single cubic lattice, right? We form anions that form single cubic and the cations. But we really want to go to closest pack, FCC, HCP. But we don't really have cubic hole. So the consequence is such that the cation forms closest pack. The anions form single cubic. Because the ratio is greater than cubic hole, right? Ratio 是0.752，但是我们 artificial hole 不可能放得下，所以这个结构就不能在 closest pack， 它不能是 HCP， 也不能是 HCP， 因为你的 cation 必须得要放在 cubic hole。所以 consequence 是什么 ？consequence 是那我 anion 就 rearrange 好了，我把我自己 rearrange 成 single cubic。对不对？看出来这是 single cubic。The consequence of this ratio that is larger than artificial hole even larger than the lower bound of cubic hole such that the anion can no longer crystallizes in the closest packed structure. Sulfide, FCC, HCP. Sodium chloride, chloride in FCC. Well, for fluoride here, because it's too small, it won't hold calcium too large inside the closest pack, such that fluoride needs to rearrange itself into simple cubic. Right, this is the simple cubic, as you can see, formed by the yellow. And the cation calcium then occupies the cubic holes half of the time. So this is the cubic hole. It's not occupied. The second cubic hole here, right? You can imagine another 4 atoms here. Occupied. Shift here, another cubic hole here, another cubic hole here, another cubic hole. 为什么？因为我们的 ratio 是1:2。Cubic inside a simple cubic, the effective number of atoms of fluoride is 1. But for every 1 fluoride, we can only have half calcium. So this calcium can only occupy half of the cubic hole. So instead of this one, it occupies this one. Instead of this one, it occupies this one. Instead of this one, it occupies this one. So it occupies every other cubic hole. Right. So you can imagine we have another cube here, formed by the yellow, and that's the body center of that cube. Another cube, formed by another more yellow here, another body center. 这部分有听懂吗？这部分每一次考试大家都会，大家都一脸疑惑。好，哪一个部分没有听懂 ？So which part that was not good？ 全部吗？好。首先 fluoride 在 simple cubic 这点 OK 吗 ？Do you guys agree with me that the fluoride is inside a simple cubic? It forms a simple cubic structure, right? Of course, this is a simple cubic, right? Okay. And from the ratio we just calculated, we know the ratio of calcium to ratio of fluoride is 0.7552. So that means calcium must occupy the cubic hole of fluoride. So right now, fluoride is inside a simple cubic structure. This structure has 1 cubic hole, right? Remember, we already write it. It's right here. But the ratio is such that for every fluoride, we can only have half of calcium. So that means we need 2 unit cells in order to hold 1 calcium, right? Otherwise, the ratio will be wrong. So this unit cell of fluoride cannot hold calcium because the ratio is 2:1. But we can have another unit cell, and we just translate this over, so we have another one here. And this single cubic can hold a cubic hole of calcium. 所以那个结构就会怎么？再往上转了。结构就长这样，就是 this is a single cubic, this is a cube, and fluoride F minus will take up the vertices 1, 2, 3, 4, 5, 6, 7. I'm not going to draw the 8. It's going to be no. So this is a simple cubic. Why? Because it has to arrange it into simple cubic. Otherwise, we don't have cubic hole. Calcium will never fit into octahedral holes. The octahedral hole is too big. So fluoride rearranges itself into a cube. And we have a cubic hole here, right inside the cube. But remember, the effective number of atoms for a single cubic is 1. So that means in here we have 1 fluoride. But the ratio is calcium fluoride 2. If we fill the cubic hole, then the ratio will be 1:1. It will be wouldn't be 1:2. So what happens is we can then translate this over. So we have another. Of course, we can have another set. Right. 1 unit cell, the other single cubic unit cell. And right now for this unit cell, we can have a calcium. Such that 2 unit cells having 2 effective fluoride, 1 fluoride, 2 fluoride, will have 1 calcium plus. And if you finish this whole thing, 1 here, another here, another here, another here, another here, 1, 2, 3, 4, 5, 6, 7, 8, 然后你把它整个画出来，你会发现 calcium 本身就封闭 FCC 啊。So if you finish this whole thing such that every other unit cell has a calcium in the body center, another calcium in the body center, another calcium in the body center, another calcium in the body center, and of course, we have diagonal, another closing diagonal, another closing diagonal, another closing diagonal. And of course, this diagonal going this way, Kelton here. This whole Kelton lattice happen to be FCC. So that's what you see here. Diagonal, 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 diagonal. Left, right, top, bottom, towards to the edge. You can another one here, 0, 0, 0, 0, 0, 0, 1, 0, 1, 0, 1, 0, 1, and happen to be FCC. So what we're going to say is this is a fluoride structure with the fluoride anion in simple cubic, and zinc 2+ occupy every other cubic hole. And zinc happen to be in FCC structure. So you can also say zinc cation forms a center cubic with fluoride occupying every tetrahedral hole. Same thing. 这就是看你是看谁哦，你是看红色的球来决定 holes， 还是你是看紫色的球来决定那个 holes。 But regardless, when we calculate ratio, it's always cation anion. You might ask the question, what if we have a huge cation and we have a small anion? Well, that's what I was talking about, anti-ferrite structure where it's fluid. But we're not going to talk about that. 我知道东西非常多，所以为什么我说这个 tensor 真的非常难，因为要背的东西很多。它其实有它的逻辑啦，它其实都是物理的作用力，然后就是一个几何逻辑在里面，但是它推导的东西非常非常多。So that's why I said liquid solids are really hard, because there are so many things to memorize. The reality is these are not numbers you memorize. This really falls within the rules of geometry and electrostatic interactions. But that's okay. If you don't like math or you just think this doesn't fly with you, that's fine. Just memorize the numbers. Please memorize the numbers. All right. And of course, just like for pure metals, we can have interstitial alloy, we can have substitution alloy. For organic compounds, crystalline materials, we can have defects. Right? We can have lattice defects, and we have multiple types. We can have point defects, where we have missing particles, or we can have particles in non-standard locations. So we have two types of point defects. Missing particles, so the ratio is no longer 1 to 2. It's going to be 1 to 1.9, or 0.9 to 2. We can have a particle in a non-standard location. You can imagine this is very easy to get, right? Zinc sulfide, we have 8 tetrahedral holes, but we only occupy 4. So we can have this shift over to the front, this shift over to the back. That will be non-standard location. Right? So we have two different types of defects. Okay? And now we can name it. So we have lattice defects, and of course we have a bunch of lattice defects. One very simple type is called point defects. For point defects, there are two subcategories, missing particle and particle in non-standard location. And missing particle has another name that is called Schottky defect. Schottky defect, that is we have missing particle. Right? So you can imagine we should have a cation here plus here, and we have anion here minus here. So by losing a plus and minus, we don't change the overall ratio, but we just have two missing holes. And these defects are very important. Why? You can imagine the band structure here will be different, so you can actually have so-called defect engineering. Excuse me. And we have another one that is migrating to a non-standard position. Both of them are point defects. And migrating to a non-standard location is called a Frankel defect. Frankel defect, which is common for silver chloride, zinc bromide, silver chloride, silver bromide, silver iodide. Basically, you have the cation just migrate to a weird location. So these two types of defects are very important to memorize. Both are point defects, Frankel defects, Schottky defects. I still have 5 minutes. Should I start? Okay, why don't we watch a video and have a rest? 好，那最后其实最重要的目的就是到 phase diagram。你刚才其实已经看过了 ，zinc sulfide 有2个 phase， 但是都是 solid phase， 对不对？我们有 liquid 跟 gas。So we're going to take a video, watch a video, and relax, and then finish this class, right? And then next class we'll finish. Wednesday we'll finish gas and phase diagram, and we'll close liquid solids. That means the quiz will open at the end of the class on Wednesday. You have 5 days to finish. And for people who arrive late, remember for this class we are actually getting to the middle of the whole course, and we have one unannounced pub quiz. will just be like your exam. 25 questions. The TA will hand out the exam at the beginning of the class and also the answer key, so you can actually fill out the circles in the answer key. If you arrive late, that's fine. You can still get the exam from the TA. You will just have less time to finish your exam. If you don't even come, then unfortunately you won't be able to get that 5 points. And as you can imagine that I'm reminding you, that means the pop quiz probably will occur soon. So remember, we still have a pop quiz for this class. Alright? So the video we're going to watch is called Regulation. There's something very interesting about phase diagram, about water. 所以大家没有想过，人类或者生物之所以可以存在，不是偶然，是因为水真的很奇怪。水为什么很奇怪？是因为它的 phase diagram 跟其他都长得不一样。它 phase diagram 长得不一样是什么？因为它的 density 在收的时候比 liquid 来的更低。也就是说，水结冰的时候会飘上来，而不是从底部一直往上结晶飘上来，这不正常。你看甲醇、乙醇也好，你喝的酒也好，你会发现它都是从下面往上结晶。如果它从下面往上结晶完成之前，到冬天湖里面的生物全部会冻死，因为整个就结成冰块。那由于水的 density 冰块 density 比较低，所以它会飘上来，它会怎么样？它会形成一层 isolation layer， 所以下面不会继续解冻，所以水生生物才可以活着，我们才可以从水里慢慢的演化到陆地上。那由于这个 property， 所以当你 apply pressure 的时候，它会从固态变回液态，所以你其实可以 apply pressure 来切冰。这个不是很正常的 phase diagram， 这是水特有的 phase diagram。所以 regulation 的意思就是 ，so the idea behind regulation is because of the phase diagram of water is so different from the rest of the substances. If you apply pressure, solid water becomes liquid water. So you can actually cut a piece of ice with pressure. This is not common. Only water has this kind of phase diagram, and that makes life possible. Otherwise, lakes will just freeze over. Right? 好，那今天就到这里哦，因为我也没时间了。好，是 Wednesday 我再把它上完。So we're going to finish the class on Wednesday. So the answer key for today is NTHU. So that's all for today. After filling the key, you can just